So while editing this episode of The Hacker Mind on self-healing operating systems, I was reminded of an article that I never finished for Forbes.com. It was on a project that Dan Kaminsky presented at Disclosed 2019. He died prematurely on April 23, 2021. Maybe I'm thinking about Dan because of that anniversary. I first met Dan when he was literally saving the world. Okay, at least saving the internet as we know it today by disclosing to the major ISPs of the world a flaw that he had found in the domain name system, or DNS. It's the translation from, say, Google.com to a series of numbers that is the physical location of the server responding to internet requests. Dan found a flaw that could have crippled the entire internet. For some reason, shortly after that disclosure, Dan gave one of his first interviews to me at CNET. Over the years, Dan continued to do really great things, like he created an app for people with color blindness called the Dan Cam. Using a variety of mechanisms, it allows color-blind people to determine the colors of objects around them. One of the last things that Dan presented at Disclosed 2019 was a time machine. He called it TimeStone. It was not a literal time machine, but a way of capturing software development process by recording intervals and storing them in the cloud. Then, when a vulnerability was discovered later on, a developer could simply go back in time and find the moment that the fault was first introduced into the code. In the unfinished Forbes article, Dan said, quote, "The reason that software is so inexpensive, we are actually very good at estimating development time. But if there's a problem, the problem is exponential with the amount of crap we're working with. And we're working with a lot of crap. I'm tired of being Sherlock Holmes," unquote. The idea that you can isolate a change and then fix a specific vulnerability, well, that harmonizes with the general topic of this episode. Rather than restoring from a backup the entire operating system, which gets you everything up until the moment that the backup was made, what if there was a way to isolate and specifically roll back the one or two things that changed? Kind of like a time machine, only it's actually much more. It's a radical rethinking of how we view our current choices of Unix-derived operating systems. And in a moment, I'll introduce you to someone who may have found the next generation beyond our current Unix-based systems. I hope you'll stick around. Welcome to The Hacker Mind, an original podcast from For All Secure. It's about challenging our expectations about the people who hack for a living. I'm Robert Vamosi, and in this episode, I'm exploring a novel database operating system, one that promises to be disruptive in how we mitigate malware today. What is an operating system, and how is it different from any other piece of software? Well, an operating system, it manages all the hardware and all the software on a given system. So what do we mean by managing all the hardware? It manages the physical resources that are needed, such as the random access memory, or RAM, or the hard or solid state drives. And the software? Well, it's your applications, it's your browser, it's your streaming media. This might seem obvious, and yet there's a point to this discussion. The first digital systems simply ran the software directly, meaning a given system ran one program at a time. And that program then handled all the issues of hardware and software. No need for an operating system. Over time, that proved not to scale. For example, you would need several different systems, each running just one program to accomplish a single task. In the 1950s, we started to get early operating systems. And these included supervisory programs that helped manage the data coming in and going back out. This started to get us to having more than one program running at the same time. By the 1960s, it was clear that multiple programs were required, and you needed to have time sharing of the central processor, or CPU. So one of the first operating systems was known as Multics, because it allowed multiple programs to run on the same mainframe system. This was superseded by UNIX, which survives to this day in one form or another. So what's the point of all this? What if we could further evolve the basic operating system beyond just managing the resources so you could run more than one program? We've done that. But now we have security issues that weren't really seen back in the 40s and 50s and 60s. So what if we could get an operating system that might help mitigate malware? So at RSAC 2023, I met up with somebody who's launching a self-healing operating system designed to do just that.
Hi, I'm Michael Coden. I'm currently Associate Director and a co-founder of MIT's Cybersecurity Research Consortium, which is called Cybersecurity at MIT Sloan, which is cams.mit.edu. I'm also a senior advisor to the Boston Consulting Group, BCG.
Michael has quite the pedigree.
From 2016 through 2021, I was the head of the cybersecurity practice at BCG. I did a lot to build that practice over 6 years. Prior to that, I was with an Israeli software company, a cybersecurity software company, and a practitioner dealing in software for critical infrastructure, working with companies such as GE Healthcare, Motorola Cellular Communications Network, industrial automation companies like ABB, Honeywell, Rockwell, Schneider Electric, Yokogawa, oil companies like Shell Oil, and so on. And I did that for 13 years. And because of my involvement in critical infrastructure, I was asked by the White House to assist in developing the NIST cybersecurity framework in 2013 in the Obama administration. And in 2014, when we published that, that's when I went back to MIT to a former classmate, actually the guy who lived across the hall from me in my dorm. And we co-founded the CAMS, Cybersecurity at MIT Sloan. And we have about 23 sponsors for that. Companies like Verizon, Google, Microsoft, State Street Bank, Liberty Mutual, BNP Paribas, some oil companies. And then through our work at MIT Sloan, we also get very much involved with the Computer Science and Artificial Intelligence Laboratory, which is CSAIL. And that's where I met Mike Stonebreaker. And that's where the story of the database operating system, this revolutionary upside-down operating system technology begins.
So on a laptop or even a phone, there's an operating system that allows you to download applications and run them. On a chip, there's something called a real-time operating system, or RTOS, which executes specific commands. And in the cloud, there are microservices that perform workloads. So before we get too far into this discussion, let's define an operating system. What makes something an operating system after all?
A great way to start. Great question. So an operating system provides a few basic services to an application. It's a file structure, inter-process communications between different processes, communications in and out of the machine like TCP/IP, something like that, and scheduling. And the original operating systems that were developed like in 1969, 70, 71, UNIX, and shortly thereafter Linux, they ran on a single CPU, and they would have a few kilobytes of memory. So I want that to sink in. So I'm old enough that I visited Bell Labs, and I've seen and involved with Ken Thompson and Dennis Ritchie, who developed Unix, on a PDP 1145, which had a single CPU and somewhere between 64 and 128 kilobytes of memory. So that's what an operating system was supposed to do. And now what has happened is we've got much more massive hardware, much more massive memory, much more massive applications. And so the operating system is being asked to manage resources that it was never designed to do.
What Michael is suggesting is that we've outgrown our current operating systems. We've reached some logical limitations on what we can expect going forward. So a new way of thinking about operating systems, well, it might be necessary. hence the database operating system.
The way that the database operating system concept was born was my colleague Mike Stonebreaker, who is professor at MIT, and he won the Turing Award for developing a lot of relational database technology. He invented Ingress, Postgres, Illustra, which became Vertica, OLTB, and other relational database technologies. And he was talking to another one of my colleagues in this database operating system project, Matej Zaharaya, who was the creator of Spark. And he is a co-founder of Databricks. And he was discussing or presenting a paper, I think, and Mike was in the audience, although they know each other very well, about how there were millions of different state variables that needed to be kept track of by the operating system, and was getting so cumbersome that they actually exported all the state variables into a Postgres database in order to manage the operating system. And so this kind of created the spark, and Mike starts thinking, and this is 3 years ago. And now I've been working with him for almost 2 years, and the team of 20 has been together for close to 3 years. And we've developed even a prototype to prove all of these things that I'm going to talk about.
Michael and his colleague, Mike Stonebreaker, will both be presenting a talk on self-healing operating systems at RSAC 2023 in San Francisco, California. And whether or not you can attend, he's very interested in getting your feedback. For example, you can go to dbos-project.github.io for more information on this open source project and test it out for yourself.
But basically, the fundamental issue is we look at that early Unix and Linux operating systems that were providing these very basic services that are still the only things we really need from the operating system today. The operating system has grown because we want to use multi-cores. We had Kubernetes, we had containerization, we had all kinds of security protections, different things. It's become a massive piece of code and a lot of bolt-ons. And it's actually managing 1 million times more state variables than it had to manage 40 years ago. So as Mike likes to say, without me saying a further word, that's a database problem. So the operating system has become something that provides these very straightforward operating system services, but it's also become a very inefficient database management system. And so that's where we came up with the concept of, well, why don't we do away with the operating system and put a database management system directly on bare metal or the hypervisor, and then run the applications in the database as stored procedures. And all the log files are stored in the operating system. So application logs, database management logs, and OS logs are all structured in the same format, stored in the same database, which is the operating system.
I just want to let that sit a moment. A database operating system, a database to manage all the services and resources of an operating system. There are some immediate benefits to this. One is performance.
From the database guy's point of view, this was like, the performance is amazing, right? When I heard about this, I said, oh my God, with SQL queries, I can do anomaly detection and detect cyber attack with simple, really fast SQL queries.
There is something here. All those endpoint detection systems, they take time to filter through all the subsystems and arrive at error reports. With a database operating system, you'd know within microseconds that you've been attacked with malware.
And we actually did some tests comparing data we've gotten we have 3 partners, commercial companies that have provided us with sample data and applications. And we've run tests of our data versus the most used external analytics engine, which will remain nameless, but it's awfully expensive. And whereas extracting all the log files, converting them to the same format, putting them into the analytics engine, running the analytics engine, you're about a 4-hour delay until you can detect an attack. And inside the database operating system, we put the same logs and we run our SQL queries, and we're talking like hundreds of milliseconds to detect the attack. We basically converted these very complicated analytics engine rules to simple SQL queries, much easier to write and much faster to run. So that was the first thing that caught my attention. And the second thing is, in databases, we have the ability to roll back to a previous state.
Let's pause here for a moment. Roll back to a previous state. That doesn't mean to restore from a backup, because there are other parts of your systems that may be doing other things. No, rather, you can roll back a very specific part of your database, leaving the rest of it intact. This is a novel approach to handling malware.
So rather than restoring from backup files, which are stored somewhere, we actually we have a function within the database operating system concept that's called provenance. And using a simple feature of typical databases called change capture, you keep a log file of every data element that's touched and what happens to it. And then you can rewind through this log file or this provenance file, and you can, within a few seconds, get back to the pre-attack state. So all the logs are kept in the database. SQL queries detect the attack. We let you know about the attack. You block the attack, and then we rewind the operating system to the pre-attack state. And you're often running business continuity in seconds. And then to carry this to, just to add a sidebar on this, my personal work, I have my other work that I do, some other hobbies that I have are worrying about the balance in cybersecurity of resilience versus protection, and the fact that you're building, you just can't protect yourself against everything, and so companies have to think more about how can I quickly recover, and that's what really attracted me to this concept of the database operating system. And it also goes a little bit further, and I've been talking actually to members of Congress about this. We can come up with a cyber deterrence concept, which would be deterrence on the basis of denying benefit. So if my system, if I can be attacked by ransomware and I can detect the attack in seconds, recover in seconds, and the adversary gets no benefit from having attacked me, they'll eventually stop.
So this anti-malware aspect of it is pretty interesting. There's a whole industry built up around signature files and heuristics in looking for malware that's on a system. But if you could detect it right at the instance that it hits your system, that's going to be pretty disruptive.
If you think about it, if we're going to have all the OS logs, all the database management system logs, all the various application system logs, all in tables in the operating system, over time, that's going to get to be a pretty big table. So what we do in the open source systems is we spool that table to a column store. So the one we use is Vertica, because Mike Stonebreaker developed it, but you can use open source ones like Redshift or Snowflake. Doesn't matter. But the interesting thing about that is that these column-oriented data warehouse DBMSs are extremely fast at searching. And that's what gives us the hundreds of milliseconds to detect an attack. time. And it's being done not in the operating system, but adjacent to the operating system in a column store database. So it's because the data, you want to look at data over long periods of time.
Anyone who's worked with databases can tell you that they can sometimes be maddening. Now, we're talking about an operating system that keeps track of everything in a database.
We did some tests against one of the most, as I said, against one of the most well-known, we got a test license against one of the most well-known, most expensive analytics engines. And, by the conversion of the logs was so complicated. The writing of the rules is so complicated, but it took between the conversion time and the processing time hours to detect an attack. And because all of the logs are in the same log file, and so if you think about it, today when you send your logs to a SIEM, you've got many applications running, and they each have their own log file. And the database has its own log file, or multiple databases, and the OS has its own log file, and they all have their own timestamps. Okay, so in order to determine an attack, you've got to merge these
and sync.
Yeah, because I want to know that Rob was trying to get to this data from New York and from Bosnia at the same time, right? That's a problem. And so the fact that these are all pre-structured, they're all in the same file, this, in chronological sequence, all in the same table, sorry, in chronological sequence. That's what helps make the searching and the detection so quick.
The granularity of this with regards to malware is pretty cool. It's like the original operating systems were built to simply run multiple programs. It wasn't until we connected these machines up to the internet that we started to see abuses on a large scale. Now, with a self-healing operating system, we've matured to the point where maybe we can deal with these modern problems.
The unified logging is really, really important. The files, messages, database scheduling, it's all in one place. The built-in rapid attack detection. We've also developed machine learning tools that look at the logs and generate the SQL code. So we can actually, the system can learn. We've been experimenting now with ML. So the system actually learns what's an anomaly, in addition to all the hundreds of rules that are typically written into a SIEM. And the built-in data governance for GDPR or the CCPA, California Consumer Protection Act. And then the fact that the programming is easier. We developed a time travel debugger.
And now you see why I was thinking about Dan Kaminsky's unfinished project. It's essentially the same, but in a database operating system instead.
So what's the worst bug that you can have in your software? The one you cannot reproduce. We call those Heisenbugs. And they usually involve race conditions. So your customer calls you up and says, here's this code, I have a bug, and you can't reproduce it. What do you do? So what we can do because of provenance is we don't try to reproduce the bug. We roll back the system and re-execute the bug. And we're able to debug software in a fraction of the time that it takes using conventional.
So we talk about the database operating system being more secure. I'm wondering, how does it handle something like ransomware, where it goes through and encrypts individual files, changing them?
If someone were able to get into the system, as I assume eventually they will be able to, the SQL rules that are scanning the logs should be able to determine that there's, in a ransomware case, there's probably a lot of data changes, a lot more data changes going on than normal. Somebody's trying to, say, encrypt the whole database or exfiltrate the whole database. So that should be pretty easy to figure out. Also, the actions are coming, say, from an external IP address that we're not familiar with. The same rules that you would have in any SIM system would be written in SQL in the operating system. Once we detect it, we would alert, shut down things, stop what's going on. It would be then up to the IT organization to block that attack. We're not going to block it ourselves. We alert, and then somebody has to determine what's the appropriate thing to do. We don't want to shut down the airplane in midair. Then at that point, there's a simple script which says, once the attack has been blocked, which says rollback, and you specify the number of minutes you want to roll back. Provenance will then roll back the entire state of the operating system, the entire state of whatever databases that have been manipulated back to their original, where they were, say, 18 minutes ago.
So again, this is very different from a backup. With a backup, you're going to restore the good and the bad, and you're going to have some gaps in there from the last time the backup was made.
Also, when was the backup made? Was it made today, yesterday, or last week?
Whereas with the database operating system, you're rolling back just the things that changed because you've got that log file telling you exactly what changed and how it did.
So the ability to just roll back, and then if you want to, you can even look at what happened between, say, 18 minutes ago and now, and you should be able to extract the valid things that the system tried to do from the invalid things, and even get yourself closer to real time. You said it very well. You just wind it back. You're at the most recent possible accurate state.
So we talked about how Unix is an early definition of an operating system. There's the commercial side of it. You know, Mac OS, Windows, Android. And the commercial, I would think you could abstract to get microservices and containers into the cloud structure. And then there's the other side, the embedded side, where you've got real-time operating systems, RTOS. So where does a database operating system fit into this, or does it replace it all?
One of the things, digging down a little bit deeper, is that main memory distributed databases today are multi-node, multi-core, and high availability in their basic nature. So containerization is not required. So you develop your software, you compile it. We built a programming environment. I call it a compiler, but I'm told now that's a passé term. It's programming environment. It's called Apiary, and that's open source. It's available on our GitHub site. And that takes your Java code and breaks it into a series of functions that become stored procedures in the database. So you're bringing the program to the data, which is the most efficient, performant way of doing it. So after developing your program in the programming environment, it's immediately deployable. You don't have to go through that extra step of manual containerization. So you actually can deploy software significantly faster, and the whole surface area of the operating system is much, much smaller. So by virtue of that, it's going to have fewer vulnerabilities. So in a cloud environment, we've actually run on the MIT supercomputer, which is 9,000 cores. The head of the MIT Supercomputer Center, who's a Lincoln Labs fellow, is also a part of our team, Jeremy Kepner. That's a fabulous guy, brilliant guy. And so for cloud environments, so the way our program environment compiles code is serverless. So it's similar to if you were using, say, AWS Lambda, but it's far more efficient, structured, and gives you these unified logging, and it's much faster in comparison tests against Lambda. The performance of the stored procedures in the database has been about 10x faster.
So the real-time operating systems, they too could benefit from this database structure.
They definitely could benefit for several reasons. Security, clearly one of them. And the other thing is that real-time operating systems are, to a large extent, transactional. And this is just transactional OS in its very nature. So it'd be more efficient and faster, significantly faster in real-time applications. The reason I don't jump to that initially is having this industrial background that I have. I know that there's like a 20-year life cycle on real-time operating system type equipment. And the equipment, that's a much longer life cycle to get into. But it's definitely a place where we see significant benefits, both for in areas like manufacturing, in areas like medical technology, in areas like defense technology, because of the increased security and the ability to deal with the transactional nature of those systems.
I would imagine the footprint on a database operating system is significantly smaller. So, in an embedded system, that would be ideal because it's a resource-challenged environment.
Significantly. We need to develop a relational database that's small enough. So that would require some development. But memory is cheap these days. So if you can get this increased security for a little like $10 more of memory, it's probably worth it.
So given the efficiency of this new operating system concept, given its ability to stop malware the moment it's detected, what industries does Michael think will be the first to adopt this new technology?
The earliest inroads, we believe, are going to be in financial technology and e-commerce. Those are the applications that are a lot of greenfield applications being generated all the time. A lot of personally identifiable information being collected. And this both protects that information, and there's another really important benefit to provenance. We're all familiar with GDPR and the concept of the right to be forgotten. Today, as far as we can tell, there is no good way of finding out where all the data by PII has been sent in existing software systems. But our provenance capability tells us exactly where every piece of data has ever gone. So we can go back through a database operating system and collect all. When you say, I want to be forgotten, we can go back and we can find your data at every place we've ever sent it and delete it. And prove that we did that, which is also in the provenance log. So the data governance capabilities of this system far exceed anything that's available today as far as we can tell.
Michael mentioned financial services, and the idea of self-healing is very important because, as mentioned, they've got PII, and that's something they need to protect. So I would imagine medical and other industries would also be attractive as well.
Mm-hmm. Very much so. And that also gets to the real-time operating systems, the IoT devices, embedded medical devices. But most of our embedded medical devices today are transmitting their data to cloud environments. So we'll probably start in the cloud environment and then work our way down. And but there's also a lot of work that I've been peripherally involved in patient systems. So it's a lot of hospitals are So, I mean, if you just deal with hospitals, well, first of all, the ransomware problem is huge inside hospitals. So if we can get this database operating system approach used in the systems that are, say the electronic health record systems, I think that would be a massive benefit, because that's what's been shutting down hospitals. The next generation of catastrophic hospital events is going to be when the medical technology systems, blood analyzers and the pharmacy system and other monitoring systems are attacked. A little bit more difficult because those are for a new software to get into those, because those have to be typically FDA approved. I think that's really important. But there's also a lot of development now in hospitals have a huge financial cost problem. And there's been a lot of movement in terms of developing systems where patients can take care of themselves to some extent. They can go online, they can make appointments, they can do televisits, they can get their bill online, they can pay their bill online, they get their medications online, they can get I just had my hip replaced and I get my exercises online. They send me every week this exercises I'm supposed to do. I think there's a lot more of that happening. That's new applications, they're greenfield applications, and they would be a good place for medical systems providers to try a new operating system.
So 3 years ago, Michael's colleague had an epiphany, and it made sense. As with all novel ideas in retrospect, they're incredibly obvious and simple. So I'm just curious, has this concept of a database operating system come up before in the history of computing? And what were the challenges with those earlier ideas?
The concept, as far as we know, has not. We've been publishing papers for 2 years now, and we don't see any competing research. And they're all available on the GitHub site, dboss-project.github.io. What's happened over the last 2 years, which is 2.5 years now, is we've built prototypes. The software that we're is all open source now. But we prototyped it on Postgres, which is a very well-known database, relational database management system. And it is also open source. Postgres is open source. And so we've built several different file systems, inter-process communication and scheduling systems on top of Postgres. You can run applications. The API programming environment will allow you to compile applications that will run on top of Postgres. You can actually try out all the functionality using this open source software. The wrinkle is that Postgres is kind of slow. So the performance of that operating system doesn't compare with conventional Linux Kubernetes. So the trade-off there was ease of use and good security versus performance. So what we needed to do was find a faster database. And one of the database systems that Mike Stonebreaker had developed is called VoltDB. And it's the main memory, OLTP, multi-core, multi-node, high availability database that's blindingly fast. The problem is he started a company, and he's no longer involved with that company, but the company decided not to open source the database. But we did get a license, and we built all the same stuff that we built on Postgres, we built on VoltDB, and running it on VoltDB, it's every bit as fast as Linux and Kubernetes. Some things are a little slower, but some things are a lot faster. So it has all the performance of any conventional operating system. And what we're looking at now is, because VoltDB is not open source, we're looking at a foundation DB, which is open source and is also very fast. And it's also a main memory database. And we're looking to convert everything and build Foundation DB into the database operating system approach. So there will be a fully open source version that will be available to the public.
personally have a theory about secondary and tertiary innovation, that you need that first level to saturate fully before you can get to the second level of innovation, and then the third. Because you don't really realize there's a problem until you have all that saturation out there, and you begin to recognize, oh, there's a problem. When you build that secondary system, you solve for that. And then maybe a tertiary system to solve for any additional problems. So, again, I'm wondering if we needed those early operating systems to reach a maturity point where we could see the problems with them and then come forward with a brand new idea.
I don't know. There's probably some good analogies in other areas where something, Unix and Linux were great for many years, but as the available hardware became more extensive and less costly, and as the applications became more complex, they've now outlived their usefulness, in our opinion.
So if I'm understanding this right, the database operating system could be expressed as a system of tables.
One of the revolutionary things about Unix and Linux was the use of files for interprocess communication and scheduling and different services, OS services. So the change from the previous generation of operating systems was this really novel thing that you could send files in between different processes. And what we see is that that's kind of old news. That's an old-fashioned, slow, and inefficient way of doing things. Our new mantra is that everything is a table. So let's say I want to build a file system. I have a table, a block table. I have a table for the directory. I have a table for permissions. It's just a set of tables. And then using SQL instructions, I query these tables, find out what's available, and insert my files into the file system. And I just put the information into the tables. If I want to do inter-process communication, I just put an entry in a table, communications table, and the other process takes the entry out of the table. If I'm scheduling is a table full of resources. And if I want a resource, I look and see if it's available, and I put my initials next to it, use it, and when I'm done, I take my initials away and somebody else can use the resource. And so this whole concept of, changing from files to tables is incredibly efficient and easy and fast. And so all the operating system state being in database management system tables is one of the things that allows us to recover the whole operating system to a previous state. I started out talking about how OSes have grown, by 6 orders of magnitude over the last 40 years, and that it's a database management problem. Instead of user programs sitting on top of an operating system and database sitting on top of an operating system and the operating system sitting on top of, actually, they're all sitting on top of Kubernetes, and the Kubernetes operating system, and then, or many operating systems, and they're sitting on many kernels, and that's on the silicon. And we show that the diagram that shows that we have a minimal kernel, we have a distributed, multi-core, multi-node, OLTP, high availability database, and then we have these SQL services that are the operating system services, and then the user applications are right on top of that. You can have a second database next to the operating system database. So a lot of in our study of the way people are develop their systems, there's a lot of data that they can't take out of existing databases, or that they're a database schema that they don't want to change. So we call that the application data. And so what you can do is you can have a database operating system where all the operating system state and all the log files are in the database operating system, but the application data, like the banking information or the shopping information, is still in Oracle or some other data, whatever database they're using. And so that's sitting side by side on the same kernel. And we think that's one way that people would be able to use the system. The fact that we're able to build the prototypes available for people to test. We'd love to get people to do that. We'd love to have them come to our session at RSA.
Like any novel idea, Michael is aware this is an uphill battle. To challenge the incumbents, and not only to challenge the operating systems, but also the whole security industry as well.
Yeah, I just wrote an email to a very good friend. I said, this is the most revolutionary thing that I've worked on since I developed semiconductor lasers for fiber optic communications. One of the reasons I left, I'm retired now officially, from BCG and joined this group of vagabonds, is I think this can replace, in this, have the same impact on operating systems that Unix and Linux had on, say, Windows, right? I mean, it's become a major force, and I think this is the next generation of general purpose operating systems. That's a decade-long process, though. It's not something that's going to happen because nobody's going to take all the existing software and convert it. We wouldn't expect that. And what we're looking for in open sourcing the software through MIT and Stanford is we're looking for people, the users and developers out there, to come back with us and say, and help us, either just tell us what features they'd like to see in it that we can develop, or help us develop them, as in any other open source project.
I'd really like to thank Michael Coden for coming on the show and talking about his new database operating system project, DBOS. If you're at RSAC 2023, he's presenting along with his colleague, Michael Stonebreaker, on Thursday morning. If you can't make it to RSAC this year, then check out dbos-project.github.io for more information on this open source project. The concept itself makes a lot of sense. We can't keep using an operating system designed in the 1960s for the rest of the 21st century. But whether it's a database operating system as the next logical step, that I leave to you. After all, we have to start building security in instead of bolting it on later. And redefining our concept of what we need for an operating system today and in the future, well, that's the first step. So I encourage you to try this out. Hey, if you enjoy this podcast, tell a friend. I bet there are others who like commercial-free narrative InfoSec podcasts. I have so many stories about hackers who are making a positive difference in the world. And be sure to check out Error Code, my new podcast that focuses on IoT and embedded security. Error Code is available now wherever you get your podcasts. Let's keep this conversation going. DM me at Robert Vamosi at infosec.exchange on Mastodon or at Robert Vamosi on Twitter. And tell me what you like and even what you don't. The Hacker Mind is brought to you commercial-free by For All Secure. For The Hacker Mind, I'm Robert Vamosi.